Swayam Prabha. Digital India. Educated India.
Good morning. Let's continue our discussion on the development of finite element equations for one-dimensional bending problem. So this is, as we were saying, it's a C1 continuous problem where we have to make sure that the slope is continuous between the elements. By devising the approximation, which includes the nodal value as well as the derivative of the function at the nodes, that will definitely guarantee that the slope is continuous. So this is what we were discussing earlier also. So now trying to get this the stiffness matrix from the potential energy formulation. So let's look at the potential energy. So this is the potential energy, so which consists of the elastic energy, which is m squared by EI, half m squared by EI, which m is EI d squared v by dx squared. And so this repeats, so there's a square here. And then this is the potential energy due to the applied force Q here, right? So Q has to be multiplied with the displacement, so with the negative sign. Apart from this, there are also other, if you have a long element, beam with some force here and P m naught. So the P and m naught also will take certain displacement, so they are associated with the work of external force. So that will also add into the potential energy. So that, you know, will be acting only at the end. So something like P times V at x is equal to L and m times theta at x is equal to m naught times. So, okay. So these things can be added towards the end at the nodes. So coming now to the exact evaluation of this one. So what we have here is that we need d square by dx square. So which is nothing but the second derivative of the shape functions, right? Here, whatever we have here. So that's what it is, and multiplied with the nodal displacements of the elements. So this, for simplicity, let's write it as the displacements here. So simply call it as U. U is the nodal displacements. So U, just for simplicity, so we have written UV. Okay, U we have been using of the element. So now here, so this is for the element. So what we have here is that d square by dx square so we split up this one. This is actually scalar, but we are trying to substitute this matrix here. So it is, I'm sorry, it is a transpose and okay. So this we can write as what? It's B times transpose, okay, Okay, so this now we can write it as, we can take UE out and so the same thing. Now we collected the nodal displacement out, and inside the transpose is UE, transpose will come out, and then B transpose EI, B multiplying UE, and here also we write it here. This is N trans UV, N times. So we can write this. The inside integral can be written as KE, and this where and F Okay, what is N? If you recall, N is nothing but the column vector, the row vector of the shape functions. Just like here, what we are doing here, this is nothing but N1, N2, N3, N4 multiplying V1, theta 1, V2, theta 2 in the matrix form. So N1, N2, N3, N4, we write it in the row matrix multiplied by the column vector of V1, V2, V3, V4. Okay, so now what we do here is that now of course you can recognize that UE is a column of 4, and this is 1 by 4, and this is 4 by 4. The K of the element is a 4 by 4 matrix. What is K? K is nothing but, as we said, it's B transpose TB. So B is nothing but the second derivative of N1, N2, N3, T square N1 x square, where N1 was, so 1 minus 3x squared by h squared, 2x cubed by h cubed. So it is 6 by h squared, and then 12 x by h cubed. Yeah, this is for N1, and N2 is minus 4 divided by h, 6 by h squared, and N3 is 6 by h squared, 12x by h cubed. And it's 2 by h, 6x by h squared. Okay, so these are the second derivatives of these things, and these things have to be substituted into this one, and then you have to take B transpose this one. So essentially, if you want to get B substituting into that, let us just say, so substituting into this one, we can calculate K. For example, if you want K11, so this is nothing but d square n1 by dx square ei d square n1 by dx square dx 0 to h. So substitute these things. I think I'll just give you, this is ei 12 by h cube. Okay, so like this is for K11. You can also do all other K12, for example. So is nothing but taking d square n1 by dx square multiplied by d square n2 by dx square with ei there. So thus, therefore, we completing all that. So we get Ke as 2ei by h cube 6 3h minus 6 3h 2h square minus 3h h square 6 minus 3h is symmetric, of course. So this is what is 4 by 4 stiffness matrix is concerned. So similarly, we can also derive the nodal load vector. So the nodal load vector is Fe is nothing but n transpose So what is n transpose? So it is nothing but your n appearing here again. X square by h square minus So assuming that Q is equal to constant or the element, so we can take Q out and then do the integration. So we will get QH by 2, QH squared by 12, okay. So this is the nodal load vector, okay. So this is assuming that there's a uniform load Q acting on the element. So apart from this, so of course now, okay, yeah, let's complete this. This is still not complete. So this is the stiffness matrix here. So we are looking at the potential energy formulation. So let's complete that. So we have got the potential energy of the element as this of this procedure is quite similar to our earlier potential energy formulations of the solid mechanics. So it is the same thing. So this is for 1 pi E, and if you go over all the elements, okay, so this can be written as usual, K global so here this is U is the complete set of all the displacements. So for example, if you have n nodes, so you will have 2n degrees of freedom. So each node, the deflection as well as the slope are the degrees of freedom. Okay, so that consists of U, and F is the global force vector, and K here is the system global stiffness matrix. So then differentiating with pi with respect to the displacement vector, so we get okay, so that leads to so one thing that can be added here is that if you have nodal, a concentrated force here and a concentrated moment, so they should be shown against the deflection and the moment. Let me explain it to you. So here the kg is of course the symbol assembly of Ke. So one thing that need to be explained here is that this Kg you have, what is that? V1 theta 1 Vn theta n. So the corresponding force vector here consists of, so the corresponding forces to the displacement itself here is the force, and corresponding to theta 1 it is the moment, like this. So that means that the force together with the displacement will do the work, and moment in association with the slope will do the work. So that is why you will find force when there is a deflection and the moment when there is a slope. Okay. So the moment is associated with the slope. Okay. So like this. So if you have at the node n, so if you have a P and some moment here, so they should be added for this one, F, N and M. So if you say M naught, so it should be added M naught here. And of course, this in addition to whatever force vector you have there for the distributed force. Okay. So this is the importance of this C1 continuous elements, where we require the C1 continuity, and that is issued by taking the deflection as well as the slope as the nodal degrees of freedom. Okay, so this comes to the discussion of these all both C0 and C1 continuous type of element. So let us just summarize the convergency requirements, because we did many types of elements: 1D elements, 2D elements, triangles, rectangles, isoparametric elements, and so on. Let us just summarize what are the convergency requirements. Of FEM, right? Okay. So what we say here is that, so let's assume if y is the primary variable, so phi means it can be the temperature, it can even be the displacements in the x-test, or it can even be the deflection and slope. So it can be anything. And dou to the power of r, the rth derivative is occurring in the integrand of the weak form of weighted residual statement, or even the potential energy form. So that in the functional there is an integrand there, and that integrand has a derivative, rth derivative of phi of weighted residual statement. It can be a weak form or functional. So we should make sure then I had be such that, so the derivatives up to because you have an rth derivative in the integral is present in the sense that it is non-zero and continuous. Within the element. So this is first one. That means that your approximation here phi hat be such that the derivatives of rth derivatives, okay, are present in the phi hat. And then we should also make sure that the polynomial, whatever you approximate here, should have or even all the constant derivatives. So it's all the constant. So here we are only talking about r, but we should also make sure all the constant derivatives up to r are also available. What does this mean? In phi hat E. So what is that? So what it means is that if you take a polynomial here, for example, a0 plus a1x plus a2x squared plus a3x cube and so on. So all the lower order terms like a0, and for example a0 will give you the constant state of the function, or in the case of solid mechanics, it will give you the rigid body motion of the body, okay, A naught. And then A1x and B1y, and those things, A1 and B1, will talk about the constant derivatives. So which means that they are representing the constant strain state. So that means that when the element becomes smaller and smaller, so it will come to a state where the whole element will be under the same uniform strain. So that is also necessarily present, should also necessarily be present in the function. So in the sense that if you devise a function phi hat here, so it should not miss any lower order degree terms. So for example, you cannot simply go from A naught plus A1x square and B1y square. So that linear terms are missing, so which is not acceptable. So they also should be present. So if you have these kind of, if these two are satisfied, then we say complete. The approximation is complete. So then there is one more here, the compatibility here. So phi hat and R minus are continuous at element boundaries. So this is also necessary in the sense that if you have R minus 1 continuity is maintained at the element boundaries, then rth derivative may have discontinuity of finite nature. So that's what we have been doing here in the C1 continuous elements also, where we have second derivative occurring. So second derivative may have finite discontinuity, but R minus 1 before that should be continuous. So this, if you assure that phi and all the derivatives up to R minus 1 are continuous at the element boundaries, then we say it is compatible element here, right? So the completeness requirement says that within the element, all the constant terms up to rth derivative are present, okay? So that constant states of function and maybe the strains and so on in the case of solid mechanics, they are all present. These are necessary when the element becomes smaller and smaller. So the function starts becoming uniform, more and more uniform state. And compatibility is that it should be CR minus 1 continuity is there at the element boundaries. So these are very important convergency requirements of finite elements. So these things you should keep in mind whenever you devise a new element. So let us stop it here at this moment, and we'll continue with some other topic later. So bye.